The other question to ask is, well, what if? Or why can't I have a pure proofreading polymerase with extreme fidelity and capture many of those same properties that we have tried to exhibited with the long-range master mix? And that's what we're looking to achieve with the repliQa Hi-Fi Tough Mix. I don't believe in universal solutions necessarily, and I think these two products can actually sit side by side, and in some applications, one may have superior performance versus the other, and depends on your individual needs. But this has been reported back to us by the labs that have been testing the product as really being a game changer in terms of true high fidelity polymerase. And again, this gets back to looking at eliminating that DU binding in the polymerase, and we've combined this with other processivity enhancing factors. So this particular polymerase is extremely processive, has very fast, it's very robust, it's and inhibitor resistant and able to amplify from crude samples. So if you look at sequencing data, fidelity is one of these things where depending on how you measure it, you can get widely differing results. But even in like that lac blue-white screening assay, we still see superior fidelity over enzymes, say like fusion or PFU. In sequencing data, we're seeing about a 90-fold lower error rate than TAC. Might be more like 40-fold in looking at that blue-white screen. We have been able to capture fragments as long as 24 kb. You'll see some of the data, and if you were definitely going for length, I think the long range is probably a better option, but we have done very long amplification. Again, we have hot start for both the exo and the polymerase. Proofreading polymerase, the 3' exo, you're going to get blunt ends, and this is compatible with DU-containing DNA, which does open the door for its use in applications with either UDG carryover prevention or methylation analysis, where you're looking at bisulfite-treated DNA and you actually do have DU content and you want to amplify that with high fidelity. So overall, we see this to be about 2 to 3 times faster than some of the best SSO7D modified polymerases on the market, generating higher yield, specificity, efficiency. Efficiency was measured in kind of an odd way. It was compatible. You could spike Ava Green actually into the product and use it on a real-time machine. And it's tolerant over a wide range of inhibitors. About the only inhibitor we've seen it really have high sensitivity to has been heparin, but it's withstood, crude blood or whole blood, hematin, humic acid, xylin from, say, complex plant sample matrices, and most of your other kind of classic sort of PCR inhibitor panel that you might run this enzyme against. That's kind of summarized in this panel. I mean, overall, it tends to stand out pretty high. I think, like I said, in terms of absolute fidelity, we've seen very, very good performance out of QFi and SuperFi, nudging out the fidelity of this. That said, it still does have very, very good fidelity that exceeds that of an enzyme like Fusion. But it overachieves in almost all other metrics that you may want to throw against it. So one way to look at fidelity is going to be a matter of accumulated errors and how many cycles you're running. If you're getting more product and less cycles, then you may actually be accumulating fewer errors. There was a very nice paper put out by the scientists at NEB looking at error rates in NGS sequencing, and one of the most common errors that everyone is overlooking is actually this spontaneous deamination of cytosine to uracil. So you're having a C to T transversion in a lot of templates. By running this faster, minimizing cycle time, you're lowering your susceptibility to those sorts of DNA damage. This just sort of shows the recommended cycling times provided by the different products on the market. I mean, with some things it could be very fast. Under 1 kb, you can get away with like a 1 second extension time, just bouncing it up and down. Mostly, I think it finds its sweet spot really in kind of this 1 to 10 kb range. Over 10 kb remains to be seen, really. I mean, like I said, we've done 24 kb. How reliable that is, we'll see. So Again, just this on pure DNA on a Lambda template. I say we've seen comparable performance, 10 kb to Q5, with the 20 kb achieving slightly higher yield, and in both cases doing that in faster cycling times. It's a bit of a messy data. I mean, you can clearly see that if you're looking at smaller fragments from complex genomic DNA, that the enzyme's performing exceptionally well. Longer fragments, now these were, if you remember the long PCR data, these two fragments were extremely robust and extremely specific with the long range. Probably going to need a little more optimization around with this high fidelity enzyme, but we did still manage to capture the 24 kb fragment, albeit with considerably lower yield. I think more important to look at is more common size fragments. We see it perform well and outperform these other, what I would consider to be state-of-the-art high fidelity polymerases on a wide range of kind of normal targets of varying GC content. So this again was a feedback from, again, an outside tester. He had done an annealing gradient to see where he would get best results. So overall, he was very happy, and it was outperforming his current status quo enzyme and lowering his time to actually proceeding with his protein expression experiments. One of the more interesting ones is we had a client look at this to feed library amplification for their PacBio system. And so if we look at, they had been using Kappa Hi-Fi with this is their kind of status quo, and this shows the bioanalyzer of the final amplified library. And so with a 5-second extension time using the LR-Fast, this is the high fidelity, the Hi-Fi tough mix. They were actually achieving greater product yield, broader fragment size ranges, a longer mode sequence frequency here, and more defined product. And so they're very encouraged by this, and this is one of the things that we're really looking to expand down the road with this. I was talking with another gentleman at a booth, and he inspired me to get back at the bench and take a look at Fragile X and look at how this polymerase can read through repeats. One of the problems with repeats is you have breathing of DNA during PCR, and you can have misindexing. And usually, I've seen more processive polymerases actually more faithfully capture, repeat regions. And since this is a very processive polymerase, I suspect it will work exceptionally well in that particular application area. So, just in summary. So repliQa Hi-Fi Tough Mix, we feel it's demonstrated superior performance compared to other state-of-the-art, polymerases. I think the real proof in the pudding is when you put this in people's hands and they're asking, when can I buy this? So that's one thing that makes you feel very good about the job that you've done with the product. Where we're looking to go with this down the road is we're hoping to get this out the door early Q1 next year. Personally, I want to look at more challenging applications, get a better, clearer design around primer design requirements, TMs, and how those marry to specific cycling protocols to improve your probability of success and your success rate when you take the product and you use it. Beyond that, we're looking to expand the breadth of applications, and we welcome collaborations in a variety of areas. We have a number of very novel thermostable reverse transcriptases in our development pipeline, so we think this could feed very nicely into full-length RNA-seq workflows on long-read platforms when we combine these two products. Because it has the capability of copying DU-containing DNA, it's obviously an ideal candidate to throw at methylation studies where you're doing using bisulfite-treated DNA. And we feel that it can be also serve as both for a generic and targeted template prep from crude samples, again feeding either conventional Illumina NGS workflows or emerging long-read workflows.